So this slide tells you exactly what happens with the communication in terms of the ions that occur. So the first thing that happens is the neuron stimulation causes a brief change in electrical charge. If strong enough, this produces depolarization and an action potential. The depolarization produces another action potential a little further along the axon. As the action potential continues speedily down the axon, the first section is now completely recharged. And this is usually with sodium ions. That's what actually happens. So this is a chart. This chart is just for reference. You don't really have to know it, but it gives you sort of the actual values related to the electrical charge in the neuron stimulation that causes the action potential. So in this case, the neuron stimulation causes the electrical charge to go above the negative 55 millivolt threshold, triggering an action potential. As you can see at the top, at plus 40 millivolts, we have the action potential, and as it drops down back a little lower actually than the original resting potential, it comes back up. That is the refractory period where you see this dip on the right hand side. So the last part of this part of the module we're going to review is how nerve cells actually communicate with other nerve cells. The neuron receives a signal from other neurons. Some are telling it to fire and some are telling it not to fire. When the threshold is reached, the action potential starts moving. It either fires or it does not. More stimulation does nothing. It is an all or none response. The action potential travels down the axon from the cell body to the terminal branches, and the signal is transmitted to another cell but must find a way to cross the gap or synapse between the cells. So this actually shows us what happens with the signal and the release of the neurotransmitters between the terminal button and the receiving area of the other neuron. And we talk about the little green things are actually neurotransmitters being released into that gap. What ends up happening in certain conditions like depression, some of the neurotransmitter gets taken back into the sending cell called reuptake, as you see on the far right. What is really important to realize is that some of the neurotransmitters, let's say such as dopamine or serotonin, actually remain in the synaptic gap, sort of like a prime, like getting the charge ready to, or the cell to communicate. What ends up happening in conditions such as depression that have a chemical imbalance, there is too much of the neurotransmitter taken back into the sending cell, and there's not enough left in the gap to facilitate the charge or the next signal, and we don't have enough to actually communicate. So that's what happens in depression. The popular drugs like Prozac and others that are antidepressants, they actually prevent the sending neuron from retaking too much of the neurotransmitter back into the end to leave enough to facilitate the next communication after the action potential tells the terminal button to release the neurotransmitter. And finally, neurotransmitters, they are just the chemical messengers that cross the synaptic gaps between neurons. They are released by the sending neurons. The neurotransmitters then travel across the synapse and bind to receptor sites on the receiving neuron. The neuron may or may not generate a neural impulse, and reuptake is the neurotransmitter's reabsorption by the sending neuron.